Hey everybody, we're talking about section 2.1 vectors today. So if you want to go ahead and have MATLAB open and open to the notes there for section 2.1, and we'll get started. First thing we need to do is we need to create some vectors like that we can work with, right? So V is this vector. These are the examples from section 2.1 in the notes. And we also create a scalar. Now remember, in this class, scalar can actually mean a complex number. It typically in this class, we're talking about a real number. Okay, so scalar, a real number. I just called it R, real number equals 3. And this is exactly what is set up online. Let me pause for a minute. So you can see I'm in section 2.1, and these are the vectors V and U. And so those are the ones I'm using in my examples. And you can see in MATLAB, right, I just have these values. You can see how I'm putting them into MATLAB. There's V, and then there's U, sorry, and I can run this, and R equals 3. And so addition and subtraction, so we have U plus V, and you can see the vector 7404 is the column vector, that's the answer, when we add U and V. Okay, so what's going on here? Well, first thing to know is that vector addition and subtraction happens component-wise, which means I take the first component of V plus the first component of U, and that's going to be the first component of their sum. 3 plus 4 is 7. Then I take the second component and the second component, so -1 plus 5 is 4. And then 2 plus a -2 is 0. 9 plus a -5 is 4. And subtraction works the exact same way. Notice that I'm doing UV in the opposite order. So I have 4 minus 3 equals 1. 5 minus a -1 is +1. So 5 plus 1 is 6. -2 minus 2 is -4. And -5 minus 9 is -14. Okay, and so let's get rid of the ink here and jump into MATLAB and see we can do U minus V. Okay, and you'll notice that 1, 6, -4, -14 is exactly the answer we got when we looked at this on the PowerPoint, right? Well, the next thing we're going to talk about is scalar multiplication, right? So we're going to take a value, again, usually a real number. A scalar can be complex number, but again, we're taking a number times the matrix. Okay, and what do we do when we do R times the vector V? Well, this is in fact the vector V right here. Okay, the 3, -1, 2, 9 is the vector. And if we're going to multiply it by 3, what do? We multiply the 3 by each value. Okay, so 3 times 3 gives me the 9, 3 times -1 gives me the -3, 3 times 2 is 6, and 3 times 9 is 27. All right, so 9, -3, 6, and 27 is the right answer. And if we jump into MATLAB, let me get rid of the ink, and there we go. We jump into MATLAB, and we can do the same thing. We can take R times V, and we get the 9, -3, 6, 27. So the same thing is working in MATLAB, all right? Also, I want to make this point. People were asking, a couple people have asked, wait, I don't know how to get a column vector, okay? All you do for a column vector is just so each row has to end with a semicolon. Well, if you have a column vector, there's only one value per row. So you put in the value, semicolon, and you can do it in a line. It doesn't really matter. Let's see, -1. You can do this in a line. and you get the exact same thing. Again, just semicolons between all of the components. Okay, so if you're having trouble getting your vectors entered, that's how we do it. Okay, great. So the final thing we'll talk about is a linear combination of vectors. Okay, so if we have these three vectors, vector 1, vector 2, and vector 3, then a linear combination is I take scalars. Now again, usually it's going to be real numbers, and in this case it's going to be 4 and -1 and 2. So linear combination, I take the first weight times the first vector. So I have C1 times V1, vector V1, which is 4 times V1. And then I take the second scalar, the second weight, times the second vector. So I have minus C2, excuse me, this should be a -1, sorry. So I should have gotten rid of the C2 in there. And it's just minus V1, excuse me, minus vector 2, plus 2 times vector 3, right? Because C3 is equal to 2. So I have 2 times V3. And notice that the math does work out, right? I'm taking 4 times the 5 and getting 20. 0 times anything is 0. So I have 20 plus 6, right? The 2 times the 3 gives me 6, and that is in fact 26. I take 4 times 3 and get 12, minus 2. 12 minus 2 is 10, plus 2 times 4 is 8, so 10 plus 8 is in fact 18. And you can see that this works out. So what I do is I do scalar multiplication, take the real numbers times the vector, right? And then I add the vectors. Okay, that's what a linear combination is. It's the sum of scalar products of these vectors. Okay, and why do we care? I mean, that is a good question. Why am I introducing it? Well, here are the key takeaways. First of all, vector arithmetic works exactly like matrix arithmetic, right? We add matrices component-wise, so we add vectors component-wise. All right. And again, vectors are just one column matrices. I mean, mathematically, we treat them like one column matrices. All right. Addition and subtraction happen component wise. Again, that's true for vectors and matrices because vectors are one column matrices. Third key takeaway is that scalar multiplication multiplies each value in the vector by the scalar. Okay. And then this is the reason I introduced linear combination, because we're going to use it over and over and over in this course. All right, so linear combination, therefore, is a term you should recognize and understand going forward. All right, have a good day, everybody.